Welcome everyone. Today I will talk about our system GRainDB, which is a hybrid graph relational system that we're developing at University of Waterloo. And this is joint work with my students Guodong and Nafisa Anzum. So let me motivate GRainDB by discussing the many appeals of developing a relational core hybrid graph relational system. By that I mean extending an RDBMS with graph modeling, querying, and visualization capabilities on top. So ever since the birth of our field, there has been a dichotomy of relational systems that support modeling application data as tables and systems whose core data structures are graphs or trees. And the first appeal of a hybrid system is that there is no perfect data model. Tables are very good at certain things. They've been essentially modeling legacy data. They're good at non-binary, representing non-binary relations over entities. They're good for normalization. So if you've got a database that contains a set of zip codes, days, and dates that you'd like to normalize, these are not naturally thought of as nodes or edges. But if you talk to users of graphs, there is a clear preference for the graph model by some users who find the graph and graph data structure and graph models closer to their mental model of entities and relationships. Similarly, there is no perfect query language. SQL is very popular and established. It's suitable for standard data analytics preparation in ETL, but it's also not the best language to express recursive queries. Languages of graph database management systems will contain special syntax. For example, the clean start to express several class of recursive queries, which are preferred by some users, right? And finally, if you're a vendor of a graph database management system who would like to get into vendor of a relational database management system would like to get into the graph database management system market, it is easier and quicker to essentially leverage the RDBMS and provide certain graph capabilities on top instead of building a graph database management system from scratch, right? So aside from the user preference for a graph model and query language over relational model and SQL, there is some performance reasons as well for why some users prefer graph database management systems. Now, you may agree or disagree whether the current graph database management systems do provide this performance benefits, but it is fair to say that the workloads that specialized graph database management systems are essentially tailored for do have several features that make it challenging for existing relational database management systems. So let me tell you what I mean by these graph workloads, right? So typical applications of graph database management systems will be something like a recommendation engine or a fraud detection engine on top of, say, a social network or financial transaction network or a phone network. So the data sets that these applications contain have a lot of many-to-many relationships between entities. So social networks knows a user might know many people, somebody may have called many other people, or an account in a financial transaction network may have made transfers to many other accounts, right? Now, the queries also of these applications like fraud detection and recommendation applications, they will contain many joins over these end-to-end relationships. So you might be looking for example, K-hop contacts of people, a typical query, and these joins can be actually cyclic and recursive. So you might be looking for cliques of contacts, or you might be looking for indirect money transfers in, say, a fraud detection application. And RDBMSs, typical RDBMSs were not necessarily designed for these cyclic join, recursive joins over end-to-end relationships, so they can benefit from some specialized join processing techniques, right? So the goals we have in GRainDB are twofold. We'd like to extend an RDBMS with fast join techniques for these quote-unquote graph workloads, and we'd also completely for usability reasons, provide some graph modeling, querying, and visualization capabilities to the user. So the vision we have is that we have a set of join processing techniques we'd like to integrate into the core of an RDBMS, and in particular, we are basing our system on top of DuckDB. One is predefined and pointer-based joins, which I will talk later in this talk about. The other is factorization, which is a technique to compress intermediate results over end-to-end many acyclic joins. It's a technique pioneered by Dan Altuano. It's essentially a compression technique for intermediate join results when joins are over end-to-end relationships. Another one is worst-case optimal joins. This is seeing a bit of adoption across relational systems. For example, the Umbra system has implemented this. This is a technique also for end-to-end joins, but cyclic joins, like finding cliques or triangles. And it also is a way to, it's an alternative to typical binary joins, and we'd like to also integrate several recursive join techniques. So we'd like to integrate all of these to the core of the system, so completely independent of any graph features. We'd like an RDBMS to get more competent on these quote-unquote graph workloads, and then on top, for pure usability reasons, we'd like to allow users to model part of their tables also as a graph, if that's what they prefer, and have this hybrid GSQL style query language. GSQL is the extension to SQL proposed by Tiger Graph. It's one of the best approaches I have seen, at least, of essentially merging some graph syntax with SQL, and it would allow for the parts of the database that's modeled as a graph to be queried with some graph syntax, but also seamlessly keep joining with, for example, existing tables. We'd like to support the GSQL style querying, and then on top provide these nice elegant graph visualizations that graph database management systems, for example Neo4j's Bloom front end provides. Right, so in the rest of the talk, I'll tell you about this one technique, predefined pointer based joins, that we have integrated into system, and conclude. All right. Okay, a major difference between graph database management systems and relational systems is that typical joins in graph database management systems are pointer-based in nature, while they're value-based in relational systems. So let me demonstrate how joins typically happen in GDBMSs. So over here, we have a financial transaction network between accounts, and a very simple query that asks for 2-hop transfers where the middle account B is owned by Alice. And the very typical query plan that's going to scan the B nodes, and then extend backward, which is the middle node, extend backward to incoming accounts, and then outgoing account to extend C, right? Extend, as I'll tell, is the index nested loop join operator, standard join operator in graph database management systems. Okay, so the first thing graph database management systems will do is that they will store node IDs, not the primary keys, but node IDs, which are effectively pointers in adjacency list indices, okay? So this could be forward indices and backward indices for each essentially node. It will point to the IDs of the nodes, incoming and outgoing nodes, okay? And so let's maybe demonstrate on a traditional tuple at a time processor for this query plan's behavior. The scan would scan and find Alice's node record, but put the node ID, not Alice value, into the B variable, and then using this node ID as a pointer into backward adjacency list, extend A would find the matching A nodes, IDs of them, and then similarly using one in the forward adjacency list, we'd find the outgoing accounts, okay? Right, so now this contrasts with standard join processing in RDBMSs, because this query in SQL, as I'll show you in the next slide, contains 2 equality joins, but there was never an equality comparison as such. It could be more efficient for some queries, right? The way we've integrated pointer-based joins into GrainDB is as follows. Over here, I'm showing you the SQL version of the query and modeling exactly the same data as 2 tables, an accounts table and a much larger transfers table, which is the edge table. And the first thing that the users do is that they predefine a primary key, foreign key join, in this case, joining transfers and accounts between owner and from to the system. And the system will use the RIDs, implicit RIDs, the row IDs of these tables as system level pointers as follows. The first thing is that for the foreign key table transfer table, we're going to add a new materialized column that stores the RID of every matching primary key table. So for example, rows with Alice over here, 1, 4, and 5, they get RID 1 into this materialized column, and these gray RIDs are the unmaterialized implicit RIDs. They're essentially shown for presentation. And then we would index for each primary tables, column table, primary key tables RID, the RIDs of the matching transfers in these RID indices. Okay, so over here, RID 1, which is Alice's RID, would get RIDs 1, 4, and 5, because those are the matching transfer RIDs of the transfer rows. Then we have got a rule-based query planning where we let the system generate a default plan, for this query, and DuckDB uses hash joins for equality joins. And then we're going to replace some of the hash joins with what we call SIP joins, which are modified hash joins that does sideway information passing, and some of the scans that does semi-join filtering. Okay, so we'll take this query plan, modify some of the hash joins and scans, and get this. And let me just demonstrate what would happen during runtime when we evaluate this one part of the join, which corresponds directly to the predefined join, the join that was predefined to the system, right? So over here, well, the build side of the hash join, this modified hash join, would scan the accounts as before and find essentially the row where the owner is Alice, but also pass the RID, which will be used as a pointer, write the RID in the tuple and pass it to the build side of the hash join, which would, as before, create a hash table, but also would generate, once the hash table is created, would generate some information by looking at the RID indices and find the RIDs of the transfer rows that will actually successfully join, and pass that as a semi-join filter. So in this example, T1, T4, and T5, which are the get one, because those are the rows of the transfer edges according to the index that will actually successfully join. So the scan of the transfer of the probe side only scans those tuples that are guaranteed to join. Okay, so this is a type of essentially integration we have done for predefined joins with sideway information bases. So we use RIDs as pointers, but unlike index nested loop joins of graph database management systems, all scans are now sequential. Okay, so I don't have a lot of time to present meaningful experiments, but what I'm showing you here is on the LDBC benchmark, which is the TPCH of graph database management system, comparing DuckDB, GrainDB, and GraphFlowDB, which is a specialized graph database management system developed in our group. And integration of pointer-based joins really closes the gap on LDBC between DuckDB and GraphFlowDB. There is some gap remaining, and that's primarily because GraphFlowDB implements factorization, and which we don't yet in GrainDB. Okay, I'll refer you to papers for more experiments, and I'd like to thank my students. Thank you.